Greetings, everyone. A very warm welcome to you all to this webinar hosted by the North Central Climate Adaptation Science Center, also called the North Central CASC, which is based at the University of Colorado, Boulder. I'm Imtiaz Rangwala, Climate Science Lead at the North Central CASC, co-hosting this webinar with my colleague, Heather Yoakum, who is our Stakeholder Engagement Lead. We bring you these webinars to facilitate a discussion of science, research, and best practices related to adaptation and resource management under a rapidly changing climate, with a focus on the North Central US that encompasses the Missouri and the Upper Colorado River basins. Before I introduce our speaker, a quick word on housekeeping. We are recording this webinar, and you can find all our webinar recordings on our website. During the webinar, all participants will be muted, but you'll have the ability to unmute during the Q&A period at the end. We, however, encourage you to put your questions and comments in the chat box anytime during the webinar, and we will start with those questions and comments first during the Q&A in the order they are received. We will end the formal part of this webinar at noon Mountain Time and stop the recording at that point. After that, anyone who wishes to stay on to engage in a more informal conversation with our speaker is encouraged to do so. And now I'm super delighted to introduce Dr. Shelley Crosby, our speaker for today. Shelley is currently a climate adaptation specialist for the U.S. Forest Service and was formerly a consortium partner for the North Central CASC. Shelley is trained as a plant community ecologist and paleoecologist with experience in climatology. She has worked across diverse geographies from the Western US to Southeast Asia, the Caribbean, and Hawaii. Her work focuses on understanding triggers of ecological state changes, climate drivers of vegetation dynamics, and the role of disturbance in a changing climate. She's most interested in linking science to action and uses ecological models and science synthesis to foster proactive management strategies that address ecological response to our swiftly changing environment. She received her PhD in botany from the University of Wisconsin and her master's in plant biology from the University of Minnesota. I, for one, have been quite fortunate to have collaborated with her these past few years. Her talk today is titled Rapid Ecological Change and Transformation Across the Middle and Southern Rockies During a Previous Climate Warming. Shelley, thanks so much for being here, and please take it away.
Great. Thank you so much, Imtiaz, for the introduction and for having me today. I'm really excited to talk to you guys about some work I have focused on rapid ecological change and also transformation in the Rockies during a previous climate warming. I first just wanted to acknowledge my co-authors, and you see their names here, Amanda Kissel and Patrick Freeman and Wynn Moss. And I also wanted to acknowledge the fact that I did all of this work while I was a senior scientist at Conservation Science Partners and a consortium partner for the North Central CASC. So I want to acknowledge and also thank CSP. I wanted to get started by just taking a look at some popular media that some of you may have run into in the recent past. That's really trying to get us to think about and grapple with the kinds of changes that are coming our way with climate change. So this article talked about whether this time ahead of us is the end of forests as we know them, because there's so much tree mortality due to drought and other issues across the globe. Another article talks about how an unusual wildfire in the Mojave Desert has really taken a great impact on the Joshua trees in that area. Yet another example shows that a heat dome killed more than 1 billion marine animals on the Canadian coast. And all of these things really come together to get across this idea of ecological transformation. So this idea that there's a dramatic and really an irreversible, at least on the timescale of managers, an irreversible shift in multiple ecological characteristics of an ecosystem. But the real basis of that is a high degree of turnover in ecological communities. And that's because, you know, some of the species that live in these places that we manage and that we know and love are not able to persist in this new climate context, in this new disturbance context. And that turnover in ecological communities is the real beginning of what we call ecological transformation. Blows et al. Recently just measured that rate of turnover in ecological communities globally. And you can see here across the globe, there's been a median of a 28% of species being replaced every decade. What this map is showing you is that the median is 28%. The red colors are a little less than that, around 23% in the dark red. And the dark blue colors are much faster than that. And we see this in Alaska and other high latitude places, where that turnover is about 52% of species are being replaced per decade. So this isn't a hypothetical sort of thing that we should be concerned about. This is real and it's happening today right in front of us. So these kinds of changes have really required that those of us who are thinking about conservation, those of us who are thinking about climate adaptation, really try and step up to the plate and think about how strongly nature really is changing in response to climate change, in response to other global change and other stressors. And the adaptation community has really stepped up, as you might expect, right? So just in the last 15 years or so, there's been quite a paradigm shift in terms of how adaptation professionals are really thinking about transformation and thinking about whether the ecosystems we manage will be able to persist in place. And there are tons of these out there, and there's a lot to work with. And you may see some that you're familiar with. There's the Resistance, Resilience, Transition Framework by Swanston and others. There's the Resist, Accept, Direct framework by Skierman and others. There's a lot of different ways of thinking about how we can really make decisions about transformation. So some co-authors and I tried to sit down and think about what's the information we really need at the table, at a decision-making table, if we were really going to grapple with ecological transformation. And we came up with a very generalized decision-making process that any one of those frameworks that I showed you previously could use. This one focuses specifically on RAD, but it could really be used across the board. And we know that there's a lot of information that we need to think about this. Number one, is transformation really a threat to the ecosystem you manage? How effective are resistance strategies? How durable will they be? What are our ecological futures? And moving around the horn here, the questions and the information that we really need at the table gets pretty unwieldy in terms of thinking about the social consequences. What about environmental justice and equity when we make choices about transformation? How's the best way to really even make these decisions? So there's a lot that's packed into this idea that our ecosystems are transforming in place, and what do we do about it? Today, I'm just going to focus on one tiny piece of this. Is transformation a threat to the ecosystems that you manage? And we're focusing on the Rockies. We're looking in the Middle Rockies ecoregion that you can see in this map here in blue, and the Southern Rockies ecoregion that you can see in orange. And so if you wanted to ask yourself, is transformation a threat in the Middle Rockies and the Southern Rockies? Some of your questions might be, well, where exactly is this going to happen? When is it going to happen? How quickly will that transition go? Is it going to be rapid or slow? What is the system really going to transform into? It's one thing to understand you might lose it, but what will come in its place? So I'll just pause here for a minute and get you all to think about what kind of science or information or tools would you bring to the table to answer these questions? I think there's a lot of ways you could approach this. What we wanted to do is think about empirically what happened during a previous climate warming in this location. So I wanted to just point out that there have been many previous rapid warmings in Earth's history. Here I'm showing you a graph that's pretty global, and it's thinking about the last 450,000 years. And this is showing you temperature change on the x-axis. And you can see that over time, we bounce up and down with temperature. And there are rapid warmings that occur frequently, and we call those interglacials. We're living in an interglacial right now. This is where we are. It's typically warmer. So what I want to focus on is this particular climate warming that happened about 20,000 years ago, and try and unpack and see what we can learn about how ecosystems in the Middle Rockies and the Southern Rockies responded to this previous rapid warming. So that just brings me to the outline of the talk today. I'm definitely going to spend just a little bit of time on paleoecological methods to get you all up to speed in case you're not. And then I want to really focus on the history of transformation and rates of ecological change in the Southern and Middle Rockies. And then I really want to dig into that on a landscape scale and try and understand what was the role of past climate change. What was the role of landscape features at that time? And what was the nature of ecological trajectories? If sites transformed, what did they transform into and how did they get there? What steps did they take as an ecosystem, as a set of species, right? And then I'll finally end with some future implications, not only for the Rockies, but hopefully for others in other locations thinking about climate adaptation during this time of transformation. So I want to get started by introducing you to a really amazing resource that's out there called the Neotoma Paleoecology Database. Neotoma is the genus name for pack rats. And you can think of this database as sort of, its own pack rat that has hoovered up all kinds of data across the board and across the globe. I'm showing you an image here of a map where all the pollen records are in North America. These are pollen grains you see on the left up here. And these give us records of vegetation dynamics over time. But the Neotoma database holds all sorts of natural archives that give us a great sense of history. We have insects, we have ostracods, we have diatoms, all kinds of vertebrate information. So there's a lot to be plumbed out of this database that's been lovingly curated by a really great community of folks to give us a better sense of what happened in the past and what can we learn from it. So I want to focus on these paleorecords of vegetation change and transformation, and I'll give you a short little crash course in how paleorecords can tell us about vegetation dynamics. So first on the left, these records come from either lakes or bogs or some kind of wetland sediment. You go in, you core this sediment, you radiocarbon data and understand the time period. And then within there, you can count pollen grains and quantify what was existing at that time. You can graph this up according to time here on the x-axis, and then we can see the relative abundance of each pollen type as we move along. So let's pretend that this blue pollen grain was sagebrush. And then let's pretend that this yellow pollen grain was pine. You can see that there was a great switch in vegetation at this time period from a sagebrush dominated system to a pine dominated system. We can look at all that information and we can measure the rates of vegetation change over time by thinking about the difference from sample to sample in how much the species communities have changed, the community composition. And then we can also find these moments of transformation when there was a real switch, right? From our hypothetical sagebrush to our pine forest here. So this is sort of a loose understanding of what we're doing here to gather this information across the Rockies. And I wanted to show you one example. I'm not going to get into these records for all the sites, but I want to show you one real example of a pollen record from Molus Lake in Colorado. There's a nice campground there. Maybe some of you have been there. You can see this record goes well beyond 20,000 years ago. You can see all the different pollen types across the top there. And here we did have a lot of Artemisia sagebrush way in the past at Molus Lake. Now this is a pine forest. We can look at all of this information, run some cluster analysis to try and determine where this moment of transformation was. And then we can compare that to the record of how quickly those changes happened. So you can see very clearly here, here's that moment of transformation from a sagebrush dominated system to a pine dominated system. And I can see that the rates of change really peaked. These blue dots are the peaks in the rate of change record right after that transformation took place. So putting all this together, I wanted to show you where these methods are going. So this is that example from Molus Lake. And I'm going to ask you to sort of bend your mind a little bit. I've switched axes on you. So now time is on the x-axis and you can read it like a book from left to right. We're a bit more than 20,000 years ago to the present day. This vertical line is transformation. These dots are where there were peak rates of change relative to the rest of the record. So we can see that there was one really rapid transformation that happened at Molus Lake. We can look at another place at Bison Lake, and we can see that here there were 3 different transformations. 2 of them happened fairly slowly, and this most recent one was quite rapid. So this just gives you a feel for how important it is to think about these 2 phenomena separately and try and measure them separately, but then integrate them. So that's what I'm going to do for all these sites in the Southern and Middle Rockies. We have 29 sites across this area, and I don't want to go into methods too terribly much, but I want you to just know what we did at all 29 sites. So we gathered the pollen data and the geochronology, the dating, the age information from the Neotoma through their API. We developed new age depth models using a Bayesian approach. We harmonized all the taxonomies. You know, not every pollen analyst identifies something and uses the exact same word. So we kind of put all that together. We calculated an ecological difference over time. If you're a community ecologist, you know, you use these multivariate distance measures. In our case, we used a Bray-Curtis. Then in order to identify those transformations, we used a cluster analysis with a broken stick method, but we also integrated it with expert opinion. All of these sites pretty much have published information about them and how the author interpreted them. We really wanted to bring that expert opinion into this work, and so we did. Then we measured those rates of ecological change, where we look at the same Bray-Curtis distance and divide it by the amount of time that has elapsed between samples. So how quickly are species turning over time? This uses a moving window approach, and it really incorporates temporal uncertainty. And then we identified those peak rates of ecological change. If you have questions about methods, I'd be really happy to answer them toward the end here. This gives you a general overview of what we did for all 29 sites. So now let's get into that history of transformation and the rates of change across the Southern and Middle Rockies. Here are all the paleorecords from all 29 sites. And I haven't really organized them based on time or geography or anything like that, because I don't really want to get into the individual site level details. I want to use this as an opportunity to think on a landscape scale and really sort of bring all these records together. But the first thing you can just notice is that these vertical lines, again, are transformation. The dots are peak rates of ecological change. There has been a lot of dynamics, transformation, rapid changes across the Southern and Middle Rockies. But if I bring it all together, we can ask ourselves, well, you know, just what does the histogram look like of the number of transformations versus sites? And what we've learned is that across these 29 sites, there were 60 different unique transformations. There were 21 different types, you know, from what to what was the system transforming into. The number of transformations per site ranged from 1 to 4, depending on where you were. And I really want to strongly point out that the number of sites that did not transform in the last 20,000 years was 0. So take a look at this empty spot here. There is no place in this Southern and Middle Rockies system that has not completely transformed at least once over this time period. When we try and put together these ideas of transformation, a complete vegetation switch versus those peak rates of change, this is a proportional Venn diagram. And what you can see is that not all transformations happen quickly and not all rapid changes lead to transformation, but about half of them overlap. When we try and look at what those turnover rates were over time, we can see that when there is peak rates of change and not transformation, those rates of species turnover over time weren't super high. In those times where those systems did transform, those rates were faster. But now what I really want to get to is that landscape scale information. So instead of looking at record by record by record, I wanted to roll it up into an understanding of landscape scale dynamics. And so this is a graph showing the proportion of sites. The blue is the Middle Rockies and the orange is the Southern Rockies, the proportion of sites that had peak rates of change during a particular time period. And you can see that the Middle and Southern Rockies are really moving in synchrony with each other over time. And then we rolled up to the landscape scale, the same thing for transformation, the proportion of sites that experienced a transformation at any one time. And you can see that there's a lot of transformation happening here around 12,000 years ago. It definitely aligns with some peaks in rates of change at that time. So these two variables are going to be something that I put into some models to try and understand landscape scale change and transformation. So now let's move into the role of past climate change. Now that I understand what happened on a landscape scale, I can ask questions about how climate change was involved. And to do this work, we used a modeled paleoclimate data set. This is from the Trace 21KA experiment. It's a CCSM3 climate model that is developed by NCAR. We took all that paleoclimate data and we distilled it into anomalies, like how different has climate been since 20,000 years ago? The trends, what were those rates of climate change? And then the interannual variability. And we did this in 100-year time steps over the last 20,000 years. And we used this R package StableClimb to help us gather that data. And then we used a modeling approach of boosted regression trees to try and relate climate variability to the landscape scale changes that I showed you previously. So here's an image of all that climate data that comes out of Trace 21KA. The left side is all temperature data. The right side is all precipitation data. Again, the Middle Rockies is blue, the Southern Rockies is orange. The top lines are all anomalies since 20,000 years ago. The middle lines are all trends. What's the rate of change in terms of degrees Celsius per year or in terms of millimeters per year? And then what's that interannual variability over time? So these data are the covariates in my model. And again, as a reminder, I'm going to run models to understand what drove these rapid rates of change on a landscape scale. And then another to understand what's driving landscape scale transformations. So the boosted regression tree results suggest that the anomaly in temperature is hugely important driver to landscape scale rapid ecological change. The other variables of precipitation and temperature just weren't as important. When you look at a graph that tries to really relate, what's the shape of that curve with this temperature anomaly since 21,000 years ago, and then what's the likelihood of having a rapid rate of change across the landscape scale, you see very clear threshold responses at about 2 degrees Celsius warming. So what we learned here is that a 2 degrees Celsius warming really triggered rapid ecological change on a landscape scale in the Southern and Middle Rockies. If we run the same model where our response is now transformation, landscape scale transformation, again, we have temperature anomalies being really important, precipitation anomaly as well. But let's just take a look at that relationship between the temperature anomaly and that likelihood of having landscape scale transformation. And you can see here, and I didn't say this before, but I'm looking at both T-min as well as T-max and T-mean and kind of running separate models to understand all of these things. Either way, it doesn't really matter. There's a very strong threshold response here, where at around 5 or 6 degrees Celsius warming, transformation was initiated very broadly on the landscape scale. So I wanted to think a little bit as well about other dynamics that happen past that really great warming that was initiated around 20,000 years ago. So for example, after 7,500 years ago, our climate system that we know and love really kind of established itself and settled in. And you can see here, there was very little temperature change in the last 7,500 years. But if you look at the record of rapid ecological change on the landscape scale, there's definitely still dynamics are happening, right? So we ran a regression trees model to just look at only the last 7,500 years. And here we see that there is a strong relationship between the precipitation anomalies and rapid rates of change that have been more recent. And the way that graph looks is that as precipitation becomes drier, as we get less precipitation inputs, there's a greater likelihood of rapid ecological change in these systems. So I want to move now to thinking about the role of landscape features. We think sometimes that the characteristics of a particular landscape may confer resilience or may confer some ability for systems to persist in place. So what we wanted to do was around each one of these Paleorecord sites, we calculated some landscape metrics in sort of donuts around the lake. And we looked at the elevation, we looked at Chile, which is a heat loading index. We looked at slope, topographic position index, and aspect. And here we used a Bayesian modeling approach that integrated that temperature anomaly that we know is important and asked whether the rate of change is driven in any way by the landscape characteristics. So here's an example of what those data look like for Bison Lake. The lake itself is this tiny little white shape in the middle, and we calculated landscape metrics in various concentric rings around that site. We settled on using the information that comes in a kilometer ring around the site. And then our response variable was individual sites' rates of change over time. And you can see that, there's a lot of peak rates of change here. And some sites really went crazy at various times in the past. Our Bayesian models, though, really point out that there are only very weak effects of landscape variables in this process. So if you're used to reading these coefficient plots from Bayesian models, anything that overlaps this red line of 0 is thought to be fairly weak in terms of how it affected that outcome. Across both the Southern Rockies and Middle Rockies, we see pretty weak effects. But perhaps in the Southern Rockies, aspect, for example, may be a bit important. And what we did pull out of here is that it seems pretty clear that southwesterly slopes are changing faster. They have faster rates of change over time. So that sort of brings me to this idea of ecological trajectories. So we know that these systems transformed. We know that some of them transformed quickly, but how did they change and what did they change into? To get at this, first of all, we needed to understand, well, what were those switches from what to what? So we used indicator species analysis to figure that out. But again, we also integrated expert opinion. We went to the literature for each one of these records and really understood how those authors were interpreting this vegetation changes. And then we wanted to focus on one particular change. So way at the beginning of this talk, I showed you that record from Mullis Lake, and I showed you how in the past it was an artemisia, it was a sagebrush dominated system. And then it flipped pretty quickly into a forested system. That was the case really across this landscape. Around 20,000 years ago, this landscape was a sagebrush dominated system. It was not the forest that we know of it today. And so we wanted to isolate trajectories out of that late glacial sagebrush system and really focus on them and ask what they look like. So here's what they look like. First of all, not just the sagebrush, but all of the transformations that happened across the Southern and Middle Rockies. And so you can see here that sagebrush systems were a common kind of transformation where a system left sagebrush and it went into something else. And what you can see, first of all, very clearly is that sagebrush systems don't just turn into something different that's all the same across space. They can turn into various different things. And so that's what we wanted to explore with this trajectories idea. So we put all those data in to a model that looks at, you can think of this as species space instead of geographic space or anything like that. All these systems, these are 4 different sites, started here in this quadrant as sagebrush dominated, artemisia dominated. The blue color is the oldest sample, and then it moves toward the yellow color to be a more recent sample. And we followed these trajectories for about 1,000 years. And we noticed that each site took a really different direction and had really different timing and really different dynamics depending on where you were. And so this is really interesting when we start thinking about adaptation, because as we're thinking about ecological trajectories, trying to understand them and what makes them bend and move and curve is really important because it leads us to think about how we could direct transformation and how climate adaptation can think about sort of the management pathways you might take to get to the desired condition that you as a manager are thinking about. This is work done by Dawn Magnus and some of her colleagues, where they're understanding that the system is going to transform, but at different positions along the way, you may want to pull what Magnus et al. Call a RAD management trigger, because this was the resist, accept, direct framework. So this is all about directing change. But essentially, understanding ecological trajectories really helps you think about what are the opportunities for directing that change in any particular alternative state that you think might be more desired. Okay, so I finally just want to end with some future implications. So here's an image of the historical and future climate change in the Rockies. And I apologize, we're in America, so this graph is in Fahrenheit. But I want to just point out that this is where 2 degrees Celsius is. That's that threshold I found for where rapid ecological change on a landscape scale was triggered. And here's that threshold of about 5 degrees Celsius where transformation is triggered on a landscape scale. And we could do some fairly simplistic thinking about the implications for the Rockies and say, okay, 2 degrees Celsius, rapid ecological change is going to happen everywhere. And I could even map that if we wanted to. But I want to be honest and point out that each climate warming is very unique, right? No 2 climate warmings are necessarily alike. Our previous warming 20,000 years ago, it was driven by orbital parameters. There was a lot of changes in seasonality, for example. It took about 3,000 years for temperature to rise 2 degrees Celsius across the Rockies. There was also a period of very dramatic cooling during this time. You can see an image of that here. And this was in 2 Greenland cores. It also shows up in the tropics in Venezuela. In Antarctica, we saw sort of an opposite signal, which helps us understand how the Earth was really operating at that time. there were extreme flooding events. There were also rapid warming events. Here in Greenland, this event was such that temperature rose 10 degrees Celsius in about a decade. I mean, think about that. So even though 3,000 years of time for rising 2 degrees Celsius seems like a long, sluggish, slow change, there were some really rapid dynamics that were happening here in our climate system. But our contemporary warming is really different. It's driven by greenhouse gases. We don't have those changes in seasonality that we did in the past. Additionally, we are warming our planet during an interglacial. So I showed you this graph before about these warming periods over time. I really want to stress how unusual the situation is that we're in right now, because we are warming during an already really warm period. It's really unprecedented what is happening. I want to note that it's going to take less than 200 years for temperature to rise 2 degrees Celsius in the Southern and Middle Rockies. That's very different from the 3,000 years that it took in the past. Also, this contemporary warming is really characterized by extreme drought events and wildfires. Here's an image from a paper led by my colleague Wynn Moss, and it's showing some analysis that Imtiaz Rangwala did to look at the projected changes in frequency of extreme droughts. And you can look at drought in many different ways. This is a very particular look that focuses on the evaporative demand. And so you can see that globally, the nature of our climate change is bringing much more extreme droughts. And we've noticed that drought is actually one of the mechanisms that's triggering transformations globally. This is a paper that Wynn Moss is leading that's in review that shows across an aridity gradient, it's not just dry places, but drought can trigger transformation in today's kind of climate. So what are the implications for the Rockies? What can we really sort of take home from this that we feel confident in? I can say that I feel confident that rapid ecological change and transformation are really very likely in the coming decades across the Rockies on a landscape scale. I think we can learn that landscape characteristics will possibly play only a weak role, but these southwesterly slopes may indeed change faster. What we've learned is that any one ecosystem type might transform into multiple different types of systems across space, and really thinking about those ecological trajectories might be challenging to anticipate. I want to just sort of pan out a little bit and ask how is this understanding relevant to the climate adaptation community as a whole? And I want to point out that paleoecologists have been, trying to ground this home for us for a while now. So this paper by Nolan et al. Shows that community composition, species composition had a very large change since the late glacial, just like what I showed you here, very large changes in vegetation structure as well. And when this paper ran a model to try and understand, well, what is the probability of large change in the future, it's really unmistakable to think that the threat of future transformation is truly everywhere. So what are the implications for climate adaptation as a whole? Number one, I just want us all to try and embrace, if you are managing an ecosystem and you are hoping that it will persist in place, I want you to know that transformation is coming. I hope that we can all pick our favorite framework, RRT or RAD or AAA or RRRR, and really bring an understanding of the likelihood of transformation into your decision making. This might mean you need to really deeply reevaluate goals and objectives. It provides an opportunity to brainstorm some proactive adaptation strategies. And to do this, you really have to get mechanistic, right? You have to understand what is going to trigger that transformation. Transformation is a combination of massive mortality events, massive recruitment failures. It's a lot of processes and ecological phenomena that are happening at once. If you understand those mechanisms, we could get to some proactive adaptation strategies. But also spending some time anticipating those trajectories. Where are systems going? That will help us really think about how we might direct trajectories if that's something that the ecosystem you manage is, like that's in the purview of how you manage that system. So I just want to leave us with this graphic about, what are all the information needs we require to make good decisions about transformation. There's lots of natural science that needs to be completed and focused on, and lots of social science. There's huge environmental justice questions here and equity questions here that we really need a lot of focus on. All I talked about today really was this one question: is transformation a threat to the ecosystem we manage? I want you to think about maybe how we could do that in other places, and how Paleorecords might really be a great tool to help us think about this further. Okay, with that, I just want to thank the North Central CASC for funding this work, and in general for really supporting the idea of ecological transformation and getting some science behind it. And I want to thank CSP as well as the U.S. Forest Service for allowing me to talk to you today. And with that, I'll be happy to take any questions if there's time. Thank you.
Thank you, Shirley, for this excellent presentation. Yeah, we have a couple of questions that got submitted. We'll start with those, and then we'll just open it up to everybody. So the first question from Rose Jaffe is about, how did you choose your sites? Just more details about it. But Rose, feel free to chime in as Shirley answered this question.
Sure, that's a great question, Rose. So first of all, we selected just all the sites in the Neotoma record or database that were within the ecoregions of the Southern and Middle Rockies. But then we narrowed it down. We wanted to have sort of small lakes or wetlands, because we know that small size gives us a more local understanding of vegetation dynamics. So we picked places that were less than 20 hectares in diameter, or in overall size, and that's how we ultimately selected our sites, really based on what kind of spatial scale of signal are they giving in terms of vegetation dynamics. And then we just ran with it. Whatever Neotoma had, that's what we used.
If Rose doesn't have any follow-up question regarding that, maybe I'll ask Heather. She has a question for you. Heather, would you like to just ask yourself?
Yeah, sure. Hang on, let me. Boop, there we go. So Shelley, I thought one of the most interesting things about your presentation, there was a lot, but when you were mentioning at the very, very beginning, when you were thinking about, you said something about like transformation is happening, like when thinking about like a human lifetime or management scale, that it's just happening so fast. I'm like, it will happen and we won't be able to. Anyway, I won't go on that. I'm just kind of babbling. But that, and then again later when you were showing like all of the data and sort of the rates of transformation and how those are changing on kind of this much longer like ecological, like epical type scale. And I don't really know if I have much of a question, but mostly just like trying to think about those different scales and how kind of our management scale and decision-making time scale, and then these like longer scales of what change looks like, and human adaptation to that, and how those kind of come together. So I don't know if you had anything else you wanted to add to that or say about that, but I thought that was something really interesting.
Yeah, Heather, it's an important point you bring up, the temporal scale of all these dynamics. And I mean, in general, ecological phenomena kind of take longer typically than our human time frame, right? Like that's common. But what's interesting today is, just this statistic about how quickly climate is changing. We're going to see rapid changes in our lifetime as managers of ecosystems that maybe, we wouldn't normally see, just because climate is changing so rapidly. And in pollen records, sometimes these changes take hundreds of years to play out, but sometimes they take less than 50, sometimes they take 30 years. So, I mean, I think really any rate is on the table, but especially because our climate is changing so swiftly, I think we're in for some rapid changes ahead for sure.
see more questions coming in. So I think there's a little more information asked regarding the the data and the sites, and I think John Williams may want to comment on that further. He said, John, would you like to go?
Hey, Shelley, great talk. And I work with Neotoma, so I appreciate the shout out and all the great work you're doing with it. There was a question in the chat about charcoal records. And as Shelley knows, there's lots of charcoal records that people collect at the same time they collect the pollen. So you can do these co-located fire and vegetation histories. The new thing I was going to add into that is that there's been a separate resource called the Global Paleofire Database, which has been the compendium for these charcoal records. And we're at the early stages of talking about merging the two and bringing that data into Neotoma. So that's kind of hot off the presses, a new thing that's in conversational advance right now.
Awesome, Jack, it's really nice to see you. And thanks for that. And I do want to say that when I started this project, I was working with Phil Higuera on digging into that charcoal database. And at that time, I was looking across the whole US West, and I knew that the pollen records we had, there were about 250 of them. When I went into that charcoal database, there were only 30 that were available. And so I felt like, even though we know fire is a big trigger and we could learn a lot about it in terms of how it drives transformation, I just wasn't able to put it together. So it's really great to hear that that database is getting up and running a little bit more. Thanks, Jack. That's awesome.
Right. I see Will Janusek's hands up there. Hello, will you go? Thanks.
Yeah, thanks. I just had a quick question. I guess it's a more definitional question. If you could just elaborate on the nuance between rapid ecological change and then transformation, and how those are different and what the thresholds mean in sort of related to those definitions.
Yeah, that's a great question. So when I talk about rapid ecological change, I'm really just measuring a rate, right? So it's like, I don't want to get into too much like community ecology stuff that doesn't make sense to everybody. But like, if you look at two samples over time and you compare how far apart they are in terms of the multivariate like species composition, and then you divide that by the amount of time that has elapsed between those two simple samples, that's simply a rate. It's a quantitative rate. But and there's no thresholds involved there, right? It's just a rate. But when you look at transformation, that is a statistical outcome of a cluster analysis, where it's like, we know there's a whole group of samples over here and a whole group of samples over here, and they're unmistakably different from each other. And there's a line that's drawn about where that is. So that's what I'm calling transformation. If you look at cluster analyses, often it's basically like, where's that first split in that dendrogram that separates all these samples from each other? It's a great way to identify quantitatively where transformation is. So that's how I did it. I hope that answers your question, Will.
Yeah, that's great. Thanks.
All right. Next we move to Megan Oldfather.
Hi, thank you so much, Shelley. I thought it was really interesting about the limited impacts of the topography on the findings you had. And I had sort of two follow-up questions. One, if you could go a little bit more into why you thought you saw the Southwest aspects really having the largest transformation. And then also if you looked at all into if overall topographic heterogeneity or like the rugosity of the surrounding landscape also impacted potential rates of transformation.
Yeah, thank you, Megan. That's a great question. And actually, I'd love to give a whole talk, just like spend some time on this, because there's a lot to unpack. First, what I want to say is it's really hard, actually harder than I thought at the beginning of this project, to do this kind of analysis, because that donut we're drawing around each of these sites is really, I mean, there's just a lot of variability of any one of these landscape characteristics in that donut. And I don't know how to get around that. It just is what it is, right? So first, I just want to say that the data are a little bit limiting in terms of what we can do there. But secondly, I just want to say that, and I feel this pretty strongly, the nature of the climate changes that we were talking about so long ago were just so large and big that they swamped out anything that had to do with landscape characteristics conferring resilience. It was not a force that could keep up with the huge exposure, that climate change was putting on these systems. But I think that there's a lot of work we could do to look at different kinds of landscape metrics. Like we almost consider this a pilot, trying to think about how to bring landscape characteristics into this world, but we could look at many different metrics. Like obviously there's so much data available about landscape characteristics. So I'd like to explore that a little more and see what we can do with that as we move forward. But yeah, it's not the best natural experiment. It's not perfect, but we're trying to do the best we can.
Right. Next question is from Katie Glover. Did chronology and number of carbon-14 dates play a role in site selection?
Hey, Katie, that's a great question. It didn't, although I reconstructed new age-depth models for every site. I don't think that, well, some of them probably only had 2 or 3 radiocarbon dates, but I don't feel like that was a huge issue in this particular area. But we did our best to provide the best dating we could by just at least constructing new age-depth models for all these sites. Right.
Hey, Jonathan had a few different comments, but I'm hoping it got addressed through John's comment. But Jonathan, if you have more thoughts, feel free to chime in.
Yeah, thanks. All my questions were addressed, but I do have one final question. Thanks again, Shelley. This is really just always really insightful and I think thought-provoking to, for me at least, as a more contemporary ecologist, to get these insights from the past. Yeah, when will this be published and when can I cite it?
Oh, I'm working on it ASAP, Jonathan, and I'll let you know. In fact, I might suggest you as a reviewer, so that'd be great.
That was a good question. Shelley, I have probably one quick question here is, I mean, you talked about these threshold of 2 degrees C and 5 degrees C. And you kind of mentioned that 2 degrees C is probably in the future, but much of the West, or a lot of regions in the West, have already experienced something like a 2 degrees C. Although globally, we are still just 1.1 degrees Celsius warmed. But regionally, we are warming more than this temperature. And, these thresholds, how do we take it out from this context, regional context, and say, hey, these thresholds are applicable globally. But yeah, we are probably already in a territory where there's a lot of stress that the ecosystem is feeling.
Absolutely, Imtiaz, I believe that's true. And I'm trying to think about it, I could have taken one approach with this data set and just said, hey, I'm going to map the time period, the year in which a 2 degrees Celsius threshold will be crossed in each of these pixels. And we're just going to say, okay, that's the date where landscape scale rapid change is going to happen. But every climate change is unique. It's like there's a phrase maybe you've heard before about how a man can't step in the same river twice because the man has changed and the river has flowed on. And I think this is the same here. The ecosystem has changed. It's not sagebrush systems that are responding right now. It's forested systems. So I don't know if that 2 degrees C threshold is the same for the ecosystems that live in the Rocky Mountains today. And I want to be honest about, how paleo data can really come to the table here. But I do kind of suspect that around 2 degrees Celsius, I wouldn't be surprised. Really, it'd be so cool to do this analysis globally and figure out where is that threshold for every ecosystem at every kind of time period. And we would learn a lot from that. But at this point, I think it's just really clear, given how much more rapid our climate is changing, that we should really be concerned that these changes are at our doorstep today.
Thanks. Shelley, if you want to unshare your screen, and I'll ask the next question from Helen Sofer, which is, after recognizing that predicting transformation is really hard and finding that landscape position matters only a little, which I don't know if you said that quite a bit. What do you think we can offer managers? Is your sense that demonstrating what past communities turned into helps give people a sense of permission to put their thumbs on the scale? That is direct change to a system type they value.
Helen, it's an awesome question. And I'm asking this myself. What is the utility of these paleo data? Maybe it's simply just educational, just to open your mind to the fact that these changes could happen. You know, Jack and I have a colleague named Steve Jackson who likes to say that paleoecology is like the gateway drug to really embracing what the future is going to hold. And I think that's true. But at the same time, you know, I think there's a lot we could learn about the ecological trajectories. And I think we can tell managers like, hey, expect many different things that could happen. Start thinking about ecological scenarios. Don't think you can have a single projection for what your ecosystem might turn into. You really need ecological scenarios. And yeah, maybe it provides an impetus for managers to feel more comfortable, depending on what kind of mandates they have, to think about directing change, to think about, you know, ecosystem, that community dynamics piece is really complicated, and there's a lot of stochasticity, there's a lot of randomness that happens there. But you know what? I think that's great news, because that means managers can really have a lever in their hand that is something they can use. So we can understand more about the trajectories and the various scenarios that might be there for the future. I think that is a lot for managers to sit with and make decisions about transformation as we move forward. But I'd like to hear from you guys, actually, like, how is paleo data relevant to, you know, how you're thinking about your system, and how would it help you, encourage you to make certain kinds of decisions? And that's what we're all about with climate adaptation, is getting the information on the table so we can make good decisions as we move forward.